Awesome. All right, guys. So is the page big enough? Can we see it? Great.
I can see it.
Cool. So yeah, just let me know if you want me to zoom in at any time. OneNote allows me to do that.
Aren't you already zooming in?
Damn. That's a good one. Anyways, so during my research project this summer, which went pretty good, I had to prove this inequality over here. So if x comma mu is a measure space with a positive measure, then for any f and g inside L2n of x, I wanted to prove the following inequality, right? So let's say if I ignored this term, hopefully OneNote lets me do Control Z. Oh, great. So if I ignored this term, it's probably just convexity of x to the 2n. But I can't ignore that term. I want the f minus g term to be there. So this actually pops up in something called uniform convexity, right? Now, at the time, since Terry Tao and friends have not invented a method where you can just search for mathematics like Shazam, I did not know that this result had existed in the 1930s. So I got to doing what I know best, and that is numerology, all right? So I reduced the problem into this setting where that we only had to prove the following. For any x and y in R, we have to know that this is true. And this is just because we can just replace x with f of x and g with and y with g of x, and then integrate on both sides. All right. Now we can actually change this two-variable equation into a one-variable equation since it's homogeneous. If both x and y are 0, all right, then this inequality is true. Suppose either x or y is non-zero, you divide both sides by x to the 2n or y to the 2n respectively, and writing t equals x divided by y or y divided by x, we get this equation over here. All right? And then so now, rearranging, we have that in order to show this LP L to the 2n inequality over here, we have to show this real inequality. All right. So now it got me thinking, how can I do it? Okay. And so the first guess was finding easy roots of this polynomial, we shall call phi sub big N of t. Right. So an easy root to see at first is just 1, right? So let's plug in 1. If I can go to my page. Right. If I plug in 1, then I'll get 2 to the 2n minus 1, 1 plus 1 minus 1 minus 1 to the 1 plus 1 to the 2n minus 1 to the 2n. So this is 0. And similarly, negative 1 also gives me a 0. Now, taking a cue from Vaki's talk last week, we can actually differentiate this polynomial, and then we see that the derivative also has zeros at plus and minus 1. Right? I could do the calculation if required, but I'm going to assume that we would all be comfortable doing that calculation. So now we know that t minus 1 squared times t plus 1 squared divides phi sub n of t. All right? So we have that this polynomial, which I want to show is non-negative, actually has these 4 easy roots. All right? So now how would we prove that this polynomial is actually negative? So there's 2 options. You know, one, we could use analysis and just do it in 5 lines, but that didn't cross my mind. So, and then, or 2, what we could do is, you know, we could use good old numerology. That crossed my mind for sure. And so that's why I actually have this little note on my website explaining how to prove that this polynomial is non-negative using these crazy techniques, thanks to numerology. So basically what I did is I went to Desmos and then I plotted phi sub n divided by this polynomial. So I basically removed a huge chunk, not a huge chunk of it, but at least some of the roots. And then I put a slider in n. And what I saw was a purely positive graph as I let n vary. Right? You couldn't make n very big, but then you could see through numerology that this had, after you quotient it out by this, it had to be a positive polynomial. And then so after that, what I did is I went to Symbolab, and then I calculated phi sub n divided by t minus 1 squared times t plus 1 squared for n equals 2 to 12, all right? And what popped out is that you get a polynomial of this form. So you basically have these coefficients are symmetric and they're all positive. Pretty funky, right? So now symmetric, you get symmetric positive coefficients. Now you can guess that, okay, if I can show that the quotient of phi sub n by that quadratic is always of this form, then we would be done. Because this is always positive, because the coefficients are positive. The only terms are even. And then what I was quotienting out by was actually a non-negative quadratic. Not quadratic, quartic. Quartic, yes. So anyways, so the quotient is supposed to be a symmetric polynomial with positive coefficients. And now you can ask, why is that true? Well, the reason why I have symmetry of coefficients is that a polynomial over a field in, of degree n has symmetric coefficients if and only if p of t equals t to the n times p of 1 over t. This is just algebra, right? So now note that if this guy's, which we started with, was symmetric, and this we know is symmetric, then the quotient is also symmetric because it just satisfies this algebraic relation over here. All right, cool. So now how do we show that these coefficients are positive? Does anyone have any cool tricks? I'll be honest, like I proved symmetry in a much more difficult way until I thought about giving this talk 2 days ago, and then I realized it was only these 5 lines. All right. I wish I thought about analysis before this, but
that's a good advertisement for giving you a food for thought talk, everyone.
Yeah. Yeah. So now, in order to show that these coefficients are positive, does anyone have any cool tricks to show whether coefficients are positive? I mean, I didn't have any cool tricks. So I'm just going to brute force compute it. All right. So we're going to do a bit of reducing. The first reduction I want to set is that I want to make t squared equals to u. All right. So if we look at this polynomial over here, we note that these two terms are even. They're of degree. They're of even degree. And then I have the sum of the negated, I don't know what you call these polynomials, but they're related to binomial coefficients. But anyways, after some cancellation in both of these terms, you'll end up with only even degree terms. So that's one observation. So now we're going to set t squared equal to u and make the problem a bit easier. So on setting t squared equal to u, we get that this quartic turns into this quadratic, which I promised about in the abstract. And then this big polynomial over here, well, it's still a bit scary. But then just note that it can be written in terms of u, as mentioned before. And we just have to know that these are its coefficients. And these coefficients will give us the positivity after a bit of calculation. All right. So now we want to create an algorithm so that we can find the closed form of the coefficients of the quotient. All right. So for a given p inside k adjoin u, such that u squared minus 2u plus 1 divides this, we want to calculate the coefficients of this quotient. All right. And actually, this condition is not even necessary for the algorithm. We don't need this. I don't know why I included it. So does anyone have any cool tricks for dividing by u squared minus 2u plus 1? Because I didn't, right? But once you see the closed form, you might guess of some cool tricks. So I don't have any cool tricks. So I couldn't think of any. So I guess it's Euclid time. Or Euclid, depends on how you want to say it. But anyways, we will write P of u in the following manner. Basically, the coefficients would be big B sub n. Okay, so now we're going to define this function from the natural numbers union 0, right? It's such a hassle writing union 0. I wonder if there's like just a letter for n union 0. I don't know. Some people have seen it. I've seen some people writing this like whole numbers.
I like n sub 0.
N sub 0.
Do a subscript. That's what I use.
I'll keep that in mind. So now we define this function from this set to the field, and it's the map defined by a sub ij, basically a of ij, is the degree jth term of the remainder r sub I obtained after I steps of dividing p by u squared minus 2u plus 1. Right. I should just say probably coefficient, degree jth coefficient, not term. So basically, a sub ij is the coefficient in front of x to the j in your remainder after the ith stage. So after the 0th stage of dividing, my remainder is the original polynomial. So r sub 0 is just the original polynomial. And so, for example, a sub 0j would just be b sub j, because I had written, oh wait, where did I write? Because I had written p as the sum of b sub I u to the I. So here is, a little back to the ground moment. So now we want to note that while performing Euclidean division, we have some relations, all right? And this is probably the most important one, right? I guess the trick over here is that you're fixing the polynomial you're dividing by. So there's actually a fixed algorithm for dividing any polynomial by that particular polynomial. So the remainder at the I plus 1th stage is the remainder at the ith stage minus the leading coefficient at the ith stage times this term over here times your polynomial. This is basically the I plus 1th remainder. It's how we did it in high school. You basically take the remainder at the ith stage, then you say, okay, what is the leading term of the remainder in the ith stage? Now I have to multiply the, what do you call something that's in the bottom of this? A quotient and?
Divisor?
Yeah, divisor, you're right. So, yep. So now we need to multiply the divisor by the leading coefficient of the previous remainder times the term to make it even in degree, and then you subtract it off. So this is how you get the I plus 1th remainder. Now we have the following relations, all right? So the leading coefficient of the I plus 1th remainder is the penultimate coefficient of the ith remainder plus 2 times the leading coefficient of the ith remainder. That is just the way I get these equations is I just expand this equation out, and then I use the fact that x to the j form a basis. So you're forced to get these relations. And now you also have that the penultimate term at the ith plus 1 stage is equal to the penultimate term at the ith stage minus the leading coefficient at the ith stage. All right. And for the other terms, they remain unaffected. They remain the same. And I'll give you a little example. So here's an example. Suppose we are dividing this polynomial 3u cubed plus 1u squared minus 8u plus 5. All right, then we set the 0th remainder to be the polynomial itself. And then now the first remainder, the remainder after the first step of division, would be this guy. You take the polynomial and then you subtract 3u times this. And then, so now you get this remainder 1. And then in order to get remainder 2, you take remainder 1, and then the leading coefficient over here was 7. So you subtract 7 times this polynomial over here. And then you basically get your remainder over here. Now, remainder 2 is where it stops because this degree is actually lesser than the degree of the divisor. So now note that a sub I n minus I, basically the leading coefficient at the ith remainder, is the degree n minus 2 minus I coefficient of the quotient of this guy. So by the Euclidean algorithm, we have that this equation holds. P would be equal to this polynomial times u squared minus 2u plus 1, and then your remainder. So now I guess the game would be, how can we calculate these coefficients? Right? So now we're going to note that in order to calculate those coefficients, we only need to keep track of 3 things. F sub I, which is the leading coefficient, G sub I, which is the penultimate coefficient, and H sub I, which is the penultimate coefficient at each stage. Is there even a word for second last? Bronze medalist? I don't know. Now, for all of these i's in between 0 and n minus 2, we have the following relations. Fi plus 1 is gi plus 2 fi. Gi plus 1 is hi minus fi. And hi plus 1 is b sub n minus 2 minus I plus 1. All right. So I guess I got to a big dump of math. Does anyone have any questions?
Yeah.
Yep.
You guys solve the original inequality with a much shorter way than your solution.
Oh, right. I mean, that's the point of the talk.
Okay.
I found a way to prove this so in such a long way that I can give an FFT talk about it.
Nice. Okay.
So, I mean, really, you might think that a shorter proof is better, but I'm the winner over here. I get more experience talking also.
Yeah, okay.
I'm just joking, man. Yeah, thanks for the proof. I would like to see it at the end, but I also have a short proof of this fact too. Yeah, let's see. Does anyone have anything in the chat?
Tom does.
Shouldn't the remainder have degree 1, or am I misunderstanding? Oh, that's the remainder after the first stage of division. R2 is the end remainder because it's the remainder after the second stage of division. If you're dividing a cubic by a quadratic, there would be 2 stages total, and the remainder at the end of the second stage would be the last remainder. Awesome. Yep, I mean, there's a really, really, really easy proof if you just use LP inequalities, which I will present. But I got into the math game really late, so I'm not really tricky like that. I'd rather just brute force everything.
Well, you know, it's kind of a clever use of convexity.
Yeah. It's a clever use of LP norms. So now you have all of these things, and well, now I'm in a spot I really like. That's basically linear recursion. Man, I thrive off this subject. I used to just play around with calculating the closed form of the Fibonacci numbers so much. So we're going to get into my domain. And in matrix form, it looks like the following. the leading coefficient and the penultimate coefficient are this matrix times the leading of the previous and the penultimate of the previous plus the bronze medalist coefficient of the previous. All right. And so now by induction, we can basically calculate this column over here in terms of F naught, G naught. And so since M is this matrix, we have that M to the I is this matrix, all right? And the proof is by induction. I have a funny story. Like, I could have made this longer because the way I originally calculated this form is I calculated the eigenvalues of this matrix, and then after that raised this matrix to the power via its eigenvalues, only to realize it had such an easy form you could calculate by induction. So as Richard asks, like, why is this so long, or why might this be so long? It's basically, I don't know why, man. I just spent 2 days on this. So anyways, now we have that F sub I plus 1. When we calculate this out, is I plus 2 times F naught plus I times G naught plus I times H naught plus I minus 1 times H1 plus blah, 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 blah. And you get these terms. All right. But since F naught was Bn, the leading coefficient at the zeroth stage, and G naught was the penultimate coefficient at the zeroth stage, and H sub I is defined in this manner, we have that F sub I plus 1 actually has this really nice form, right? And one can easily check that this formula also holds for I equals -1. I mean, it's basically this F sub 0 is equal to B to the N. So now that we have that, we are going to form a recursive statement about the coefficients of these polynomials. So F sub I plus 1 is equal to this. Writing it out in the following fashion, I'm just going to knock off one term from each of these summands. So over here, I take a B sub n out. Over here, I take a B sub n minus 1 out, blah, blah, blah. And then I couldn't have taken a B sub n minus I plus 1 out. So I just take it out of this line over here. But note that this top line over here is actually F sub I. And then so we get that F sub I plus 1 is F sub I plus the sum of the last I plus 2 coefficients. All right. And now we're going to calculate the positivity of the quotient polynomial. So if you set phi sub n to be the polynomial such that phi sub n of u is phi, oh god, this doesn't sound right. I should have called this psi, whatever. If you set var phi sub n to be the polynomial such that var phi sub u is equal to phi sub n of t, now we can calculate the positivity of these coefficients over here. So we let var phi sub n of u have the following form. All right. Note that f sub 0 is this number over here. Now suppose that you have I is greater than 0 and is less than the floor of n minus 2 over 2. And f sub I minus 1 is greater than or equal to 0. Right? Then we have the following holds. That's basically by this formula over here. And since the following holds, now I can use combinatorics. So I'm basically going to gather all of these terms. Sorry, this is a mistake. This should be 2i, not 2n minus 2i. So I gather all of these terms over here, and I'm summing up these binomial coefficients 2, 4, blah, 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 all the way to 2i. Now, since I'm summing up even binomial coefficients, and since I is less than n over 2, what we have is this sum is actually less than or equal to 1/2 times 2 to the 2n. to the 2n minus 1. Because we're summing up 1/2 of the even binomial coefficients. Now that gives me that if I move over that 0, 2n choose 0 to the other side, it becomes this minus 1. And now I'm summing up all these binomial coefficients, I get this inequality. So now f sub I plus 1 is greater than or equal to f sub I plus this guy minus this. But this minus this is 0. So f sub I plus 1 is greater than or equal to f sub I. Now that was if I was less than or equal to the floor of n minus 2 over 2. But now by symmetry, since we know that we have that this condition holds, we have that for all coefficients, f sub I is actually greater than this number over here. So we're done. We have proved that the quotient is actually has positive coefficients. So now we can write var phi sub n of u is equal to s of u times u squared minus 2u plus 1, where s has positive coefficients for n greater than or equal to 2. And if n is equal to 2, if n is equal to 1, then you actually don't get positive coefficients, you get a 0, I believe. And so now phi sub n of t is equal to s of t squared times this quartic. But guess what? S of t squared is a polynomial with only even degree terms whose all coefficients are really positive. So therefore, this is always greater than or equal to 0. And we're done. All right. So that's the proof of this LP inequality. And yeah, since I can't let you guys go away without seeing the actual proof of this. I found this in RP Boas's note on uniform convexity in LP spaces.
Can you go back one slide,
Go
Bob?
back.
Yeah.
Let us know, Tom.
Oh, is there a question? Sorry.
Oh, he just wanted to look for a little bit. Tom sent in the chat.
Yeah.
Also, while we're looking, Vatsa, do you know what these coefficients of S are? Like, are they combinatorially nice? Or are they just some of weird binomial coefficients?
Oh, I didn't check whether they're. Oh yeah. I didn't check whether they're combinatorially nice, but they're these coefficients over here. So basically, we can say that if S sub u was f naught u to the, what is that? N minus 2 plus dot 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 dot. Oh, sorry, I'll go back to that page. My bad. And we have these. Then I guess you could say f sub I is actually equal to, what is that? I plus 1 times 2 to the 2n minus 1 minus 2. Is it 2n minus 1? Let me go back. I just want to look at my formula again.
Yeah, I mean, it's fine if you don't get the exact thing here. I was just curious if you knew offhand whether they were nice or not.
Yeah, that's what I was thinking. I mean, it should be nice, but I mean, it really was not nice when I looked at it. So it's basically this plus I minus 1, negative 2, 2n, choose 4, plus dot 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 dot, 2 times, and then you just go in this pattern until you get to negative 2 times 2n, choose 2i.
Yeah, so I think Thomas had another question back on the previous slide.
Right. Why is it t squared minus 1 squared? Let's see. On that note, well, the thing is that this was the it was divisible by t minus 1 squared, and it was also divisible by t plus 1 squared. So unless I wrote t squared plus 1 somewhere, I don't think I was intending to divide anything by t squared plus 1. I was intending to divide things by t minus 1 squared and t plus 1 squared, which is t squared minus 1 the whole squared. Right?
Yeah, I
All right.
showed a typo somewhere. I think
Yeah,
that
yeah. We can check. Yeah, I don't know. There might be a typo somewhere. But yeah, oh yeah. No worries. It's all good. This should definitely be true because I made some C++ code and actually did the polynomial division and checked my formula, and it worked for like the first 100 numbers. So yeah. And since it's not
Math 109 at its finest.
and since it's not something like the Dirichlet prime number theorem, where it's an asymptotic formula, usually it would be true. I mean, usually it points towards it being true. But there are some things like the Dirichlet prime number formula, where, for example, the number of prime numbers which are of the form 4n plus 1 forms a larger chunk than those of 4n plus 3 for like the first, I don't know, billion numbers. I'm not sure what that is. And so there's a thing called Littlewood phenomenon, which explains why this percentage goes up and down and up and down and up and down. Okay, so now afterthoughts. So it turns out that this was actually just a thing called Clarkson's inequality. And it's actually true for anything p greater than or equal to 2. And yeah, so the way you prove it is the following. Man, this is so tricky. So first, you let this vector be an r squared. For p equals 2, the proof is really simple. I bet that just boils down to some checking. For p equals 2, it's easy. All right, because for p equals 2, you have a Hilbert space. You can just use the inner product. Then now the p norm of this vector for any p greater than 2 is actually less than or equal to the 2 norm for this vector. So we have that this holds. And now expanding what's inside, the 2xy and the negative 2xy will cancel out. And then you'll just be left with 2 of this x squared and 2 of this y squared. And so you get this, but this is just equal to the 2 norm of x comma y, and which is equal to the 1 norm of the absolute value of x squared comma absolute value of y squared to the 1/2. So this, by Holder's inequality, is less than or equal to the p over p minus 2 norm of 1 comma 1 and the p over 2 norm of this vector over here. But this is now, I just removed the 1/2. I just put it over both these terms. And then now I actually calculate what this term is. It's just this. And this term is actually just the p norm of x comma y. And now if you multiply these two terms, you actually get 2 to the p minus 1 over p. So now raising both sides to the power p, we get this inequality. So yeah, I don't know. I don't blame myself for not thinking about this. This is extreme. It seems really tricky. The easier solution, honestly, just seemed like doing this to me, but I guess to each his own, you know. So yeah, I guess I thought I would be way over time, but I guess my presentation was actually way under time. So yeah, I would like to ask if anyone had any questions.
Let us first thank the speaker by however you'd like.
Yeah, I actually did have a question. So
yeah,
should I expect to see a note coming up on Vixar or something with this numerological proof, or what?
Oh, the proof isn't numerology. The proof is good, but yeah, I can give you like, I guess I could submit the first 2 pages, you know, with this Desmos screen cap and the Symbol Lab screen cap, and I guess maybe if I just you know, drew some triangles here and there, put it on Vixra.
Okay, cool. Yeah, send me the link. Yeah.
Oh yeah, yeah, of course, and then my proof of the Riemann hypothesis is also on the right. Any other questions? Yeah, or if we have some time, I mean, I wouldn't be opposed if Richard could actually show us what he came up with to prove it.
Yeah. Yeah. So in the like first page.
Right.
So you have that like x and y thing, right? So what if you substitute a equals to x plus y over 2 and b is x minus y over 2?
If you substitute a is, oh, okay.
It's y
So
over 2.
I guess, yeah, that's why I have this explanations thing. So I guess you have this inequality over here. Wait, what's the inequality is going for? I guess it's this. Yep.
Yeah, so you let a equal to x plus y over 2, b is x minus y over 2.
Okay.
Then x is a plus b and y is a minus b.
X is a plus b and y is a minus b.
Yeah. And then you just expand, and the a to the 2n and b to the 2n cancel out on both sides, and then the other terms left are all squares.
But and the other terms left are all squares.
All positive squares. Squares with like positive coefficients.
Oh yeah, yeah, that's right. Yeah.
Yeah.
Yeah, I think this is what I did when you emailed me.
Yeah.
I like the fact that you're getting more information about the polynomial in question. That's kind of fun.
Yeah, yeah.
Thoughts, are you there? I can't tell if you're just like shocked by.
Oh, I think he's actually frozen. Okay, man, that's hilarious.
I was like, oh, he's shocked by how beautiful this short proof is.
All right, well,
Let's stop the recording.
yeah.